Hey guys, I think you're all off to a good start on your projects. Just in case, thought you might be interested in knowing that people use modeling to predict success in marriage or dating. Here's a mathematician who studied 700 couples, had a psychologist interview them for 15 minutes after they were newly married. The psychologist had the people talk in front of him on issues such as sex, child rearing, or money. And he evaluated their body language, smiles, affectionate gestures, or rolling of eyes, mocking, and coldness. So some gestures got positive points for his model, other gestures got negative points, like 3 for scorn, -3 for scorn, and +2 for humor. Then he took those points and fed them into his mathematical model, then went back and checked on the couples every 2 years and found out a 94% success rate in forecasting whether the couple will stay together. Kind of scary, almost like predestination. Maybe there's a better way of predicting whether a person would be a good person to marry. In my opinion, maybe look at how they treat their parents. So, for example, if a guy is pretty good to his mom, might make a good husband. Anyway, the last thing you want to hear from me is who to marry, advice on who to marry. But seriously, thanks for your hard work. We've gone through the first week here online, and as far as I know, we're still doing pretty well. Let me know of issues that you're having. On Brightspace in the homework and problems folder at the bottom are 2 Excel spreadsheets and an Excel and a PDF document section 3.1, 3.2. So that's the notes that I'll be working through and the 2 data sheets that I'll be using. The notes look like this. We are starting chapter 3 in the textbook, so this material will be more traditional if you're a little overwhelmed and puzzled by the neural networks things. We're getting back to very standard modeling material. When we make a model or think about making a model, we're in probably one of 2 situations. Either we have prior insight into the problem or we don't. For example, if I'm trying to model how fast a bacteria grows, then I don't know the reproduction rate of this particular species of bacteria, but we know that one bacteria divides into 2, divides into 4, divides into 8. Bacterial growth is exponential. So I might just say from the prior knowledge and theory, I'm going to use a model of the form population is, say, AE to the BX. And my job is to find the constants A and B that best match my data. But the choice of the model form was because bacterial growth is exponential. Whereas the problem I actually want to consider is when the energy usage of a particular community is modeled over time. And I really don't have much insight into that problem. So rather than pre-choosing a form of the model, I might look at a graph of the data itself and say, looks like it could be a parabola, or maybe a y equals x cubed or y equals x to the 4th form. I don't know for sure what exact form to choose, but the shape of the data suggests that I choose a model of the form, say, y equals ax to the b, where x is time here and y is energy usage here. And again, my job is to find a and b, but now they play different algebraic roles in the equation. The Excel spreadsheet 3.1 energy has this data, and I want to work with that a bit. Point to make, though, is this time scale is a bit awkward. So it's calendar years since the birth of Christ, but in terms of the size of the numbers and the spread between the numbers are very large compared to how much variation there is in them. And when that's the case, First of all, the numbers are clumsy large when I do regression and get coefficients on my equation and so on. They tend to be larger and smaller than what they would be with the more intelligent choice of variables. So good idea in this case perhaps to subtract 1900 from the years, or in other words, talk about years since 1900. So x equals calendar year minus 1900. And then just to show that you could even go farther, that's going to take these to be numbers like 10, 20, 30, 40. We could divide by 10 and work in decades instead of years. So what we're really doing here is converting time to decades since 1900. And you might have said, well, let me take years since 1910 and start at 0. Then, and by the way, the x's now are going to go 1, 2, 3, 4, and so on. I'd rather not have my x's start at 0 because for problems like this, I often want to end up using a natural logarithm, and log of 0 is not defined. So now, if I use these values for x and my consumption variable for y, so x going on this axis, y going on this axis, I do see this graph that I was talking about on the previous page. And so now my job is to fit a power function model through this data. It turns out that both our I and Excel routines are better at fitting lines than curves. And so we'll do something now called linearizing the model. So our model is y equals ax to the b, but if I take the natural log of both sides, I'll write it ax to the b, but I have a log of a product that turns into a summation, and I have a exponent here, and another property of logarithms says that comes out as a coefficient. So log of a plus b natural log of x. So now if I think about log of y as being a new variable, and log of x, capital Y, and log of x as being a new variable, capital X, my model is now of the form capital Y equals log of a plus b, capital X. This is linear, and I have successfully linearized my model. I'm still trying to find the numbers a and b. Let's go to the data. So this is spreadsheet 3.1 energy. And the values in column B are the Y values, but these are calendar years. So let's get our X values by, as we said, taking the calendar year, subtracting 1900, and dividing by 10. Drag that down. Okay, then we said, well, this has a power model form, which we will straighten out or attempt to linearize by taking natural log of both variables. So natural log of x here, natural log of y here. And natural log in Excel is ln of this number. Drag that down. And natural log of y is here. And drag that down. So supposedly we've linearized the data. Let's look at a scatter plot of the log data, and there it is. So the original data was definitely concave up. This data is approximately a straight line, and it is here. So this is ln x on this axis and ln y on this axis. Okay, so either by eyeballing or better Let's ask Excel to fit a linear model to this data. So highlight it and add a trend line. And let's have Excel display the equation. And there is our line. Let me go back to the notes and write down what we got. So Excel told us that capital Y, this is in the log variable, 2.522 times capital X plus 1.0724. So now if I compare my linearized model form with the numbers that I got, I see that natural log of A is the constant here, 1.0724. And so if I want the value of A, I can take the base E exponential and get 2.922. And for the value of B, it's the number in front of capital X. That's the number 2.522. So I have the two numbers that I need for my model. If I go back and look at my original model form, it's AX to the B. So in my original variables, Y equals 2.922 X to the 2.522. So that's what I was looking for. It's not y equals x squared, it's not y equals x cubed, it's y equals x to some power in between. And by some standard of least squares, this is the best model to use of this particular form. Let's see graphically how this does. So if I come back here, I can get rid of my graph now. And let's generate the predicted value of y. So the form that I got was 2.922 times x to the 2.522. So y equals a x to the b. And we will copy that formula down, and the hope is that the predicted values match the actual consumption. So not too bad. I can see some deviation, but the general trend seems to be working. Let's do something else. When you fit a model in this way, quite often you want to look at the errors of the model. Error or residual mean the same thing in math and statistics. So I'll call it residual here. In any case, it's by definition the actual value minus the predicted value. And if we drag those down, these are our errors. Ideally, we would like these to be 0. They never really are. And now let's see what the residuals look like. So it's often useful to look at a plot of the residuals. In general, you want to plot them as a function of the independent variable. So I will make a copy of the scaled time. Whoops, not like that. Copy and paste. Sorry, I'm not sure what's going on here. Well, I will retype them. I don't know what that was about. Maybe, oh yeah, relative or absolute addressing. Should have been more careful. Anyway, here is the data. And now let's look at a plot of what's going on here. Okay, these are the so-called residuals. This is time on the scaled time on the x-axis, which notice is right here in the figure. And then, and on the vertical axis is our error. So now if I go to the next page of the notes, here is the picture we just generated. And the question is there any trend left in the residuals? Here's the idea. If your model is the best model that could possibly be, then the residuals or errors should look random because the model will have captured all the known trend or pattern in the data. On the other hand, if you see something, a residual pattern like one of these, this is bad news because here it's telling me over time my errors are getting worse, or over time my errors are going from negative to positive, or over time there's some quadratic form in my errors. You really want your errors to be random, telling you that the model has captured all available pattern. This doesn't look too bad. There's some bouncing up and down. Here are two rather large negative values. So here we notice that the model is over predicting here. The under predicting, actually. What I'm trying to say is back here on the spreadsheet, I can get this guy out of the way, back here on the spreadsheet, that the predicted values are larger than the actual values. So I guess the right way to say that would be over predicting, and therefore that the actual value minus the predicted value is negative. But not bad overall. At least I don't see one of these kinds of patterns. Okay, let's leave that example and talk just a little more about linearization. So you have a particular form of a model that you decide to use, and how can you turn it into a linear form so that Excel trend line could be used to find the values of A and B, or whatever coefficients you have in the model. How about y equals a plus b times sine of x? Well, here this is pretty straightforward. I'm going to take capital Y to be the same thing as little y, and I'm going to take capital X to be the same thing as sine of little x. That immediately transforms this into a capital Y equals a plus b capital X form. So that linearization is pretty obvious. The second one is the one that we already did. If we take natural log of both sides, we turn this into an ln a plus b ln x form. And so if I take capital Y equals ln of my original variable y, and capital X to be ln of my original variable x. Now I get my y equals ln a plus b times x. I don't care that this is an ln a. We can unravel that at the end like we did in the example. What's important is that on one side is just the variable, the new variable capital Y. On the other side is just the new variable capital X in linear form. Number 3, now they're getting a little trickier. Suggestion here that we multiply both sides by the denominator, and then we'd get axy minus by equals x. And then suggestion that we divide both sides by a times x. So that would get me y minus, and I'll write this as b over a times y over x. I divided both sides by a times x. So this term got divided by ax. There it is. On the right-hand side, I divided both sides by a times x. So the x's cancel, and I get 1 over a. And final form then, y equals b over a times y over x plus 1 over a. So I can let capital Y be little y, and capital X be little y over little x to turn this into the form capital Y equals b over ax plus 1 over a. That one's a bit tricky, quite tricky actually. And just to point out, this can get trickier and trickier, and some problems just can't be done. So it turns out that this one cannot be linearized. I could try similar things, but eventually I have to get the x out of the exponent. When I do that, I'm going to take a natural log, but then the y goes inside the natural log, and you just can't get something of a form like this. Okay, let's go to, well, one more thing before we go to a new example. You've probably noticed when we've done regression that several options are available. So let's see, where could I go to illustrate that? If I came here and inserted another column and put my 1, 2 numbers. So I might think about fitting a model to this data without transforming. I could, for example, generate a scatter plot and get this shape, and then go to insert trend line. And you notice some other choices. So we could actually have chosen power here and had Excel display the equation on the chart. And lo and behold, there is the model that we came up with. Don't think that we were wasting our time. It actually turns out that what Excel is doing to get this result is exactly the process we went through. And sometimes the model form you want is not one of Excel's pre-programmed choices. So you still need to know how to do this scaling and linearization. But if the model form you want is already built into Excel, of course, that's a faster way. Now let's use what we know about how algebraic functions work, transformations actually work. So suppose I have this same shape of data, increasing concave up. And I'm suggesting a replacement that maybe x, capital X, could be square root of lowercase x. So this is going to be my new notation for a change of variable like this. Rather than writing down the capital X, I'm just going to say, oh, the old x goes to square root of x. Or I could take y going to square root of y and lots of other things. We'll consider other choices in a moment. But if I'm trying to linearize the data, then some choices make better sense than others. So let's think about what happens when we do a transformation like this. X is going to be replaced by square root of x. Or in other words, I take the square root of the x coordinate of each of these points. Well, some of the numbers aren't going to change very much. In particular, the square root of 1 is 1, so this point's not going to move at all. And the square root of, say, 3 and the number 3 are not all that much different in size, a little bit, but not too much. But when I have a number like 10 and I take the square root, now square root of 10 is much smaller than 10. So this effect is going to be to take these larger values of x and move them back to the left. So those points are going to land back here. whereas these points are not going to move too much. And so if you think about it, this is actually going to make the curve even more concave up. It already is concave up, and this is going to make it steeper. Whereas if I took the transformation y is replaced by square root of y, or in other words, take the square root of all the y coordinates, then again, points with small y coordinates aren't going to change very much, but points with large y coordinates are going to change a lot. They're going to get smaller in their y coordinate, and so the effect is to drag these points down here and not move these very much. And that's what I'm trying to do. This actually will grab a hold of this right end and drag it down to become more linear. So this is a much better choice if I'm trying to linearize the data. So it turns out that mathematicians have studied functions and their shapes for a long time. Here's the baseline right here, that there would be no transformation. And now we just saw that if I replace x by square root of x, something like this, that we actually increased the concavity. So it was already positive, it's going to become even more positive. And then I'm not going to go through the graphing, but these functions have the same effect, replacing x by natural log of x, or x by 1 over x, negative 1 over x, all have the effect of increasing concavity, as does the effect of replacing y by y squared or by y cubed. We didn't look at doing that, but those would also increase the concavity. Whereas these transformations down below the baseline decrease the concavity. Decrease concavity. So before, my graph was concave up, the concavity was positive, and when I applied this transformation, it got closer to 0. So it took a positive number and decreased it towards 0. And here are some other things that do that, to replace y by natural log of y, or to replace x by x cubed. So you see sort of a reverse in when I do something to the dependent variable, it has the opposite effect as if I do it to the independent variable. And there's a hierarchy here, actually. These functions are arranged in rates of growth. So to, for example, replace x by x cubed decreases the concavity more than replacing x by x squared. And so you kind of look at your graph and see which direction do I want to change the concavity, increase or decrease it, and by a little bit or a lot, and then I kind of come to this ladder of transformations and try to choose an appropriate spot. Let's look at an example. If I go now to the second spreadsheet, section 3.2, Bluefish, if I just, notice that the data started out as calendar years again, and so the choice that I made this time was that x, my scaled time variable, is going to be year minus 1940, and then now the numbers would be like 5, 10, 15, 20, and I've chosen to divide them by 5. So in this case, I'm working in like half a decade, and that makes the scale here go 1, 2, 3, and so on. Again, sort of important to get the 1945 knocked down to size. Whether I divide by 5 or not is not so important. So here the scaling has already been done. X goes from 1 to 10, and here are the Y values. This is the amount of fish in some weight measurement taken from the Chesapeake Bay in a certain time period. If I look at what this data looks like raw, it is definitely concave up. So from my model, or from my ladder, I should say, I want to decrease the concavity. And so I might try something like replacing y by square root of y or replacing x by x squared. Let's try one of those. Let's see, I am here. So I will downsize this and okay, this is actually y. So let's apply a transformation. So maybe I want to replace y by square root of y. And I can do that. And now I want to see what the data looks like. So let's see, can I do this? If I highlight this data and then hold the control key down and highlight this data and insert a scatter plot, is that going to do what I want? There we go. Okay, so the idea is this helping? And if so, is it enough? My original data looked like this. It was pretty concave up. My transform data, when I replaced y by square root of y, is still concave up, but you notice not as much so. In particular, what we had hoped would happen really is. These guys at the very end are turning very steeply up, whereas now they've been tamed a little bit, and so there's not this real bend at the very end. Okay, we could keep going and going on this. Let's just note that on sheet number 1, I've done a lot of work then of this form. So I've tried, here's our original data. I've tried taking y and replacing it by square root of y and get a figure that looks like this and say that's still concave up. I need to go stronger. So the next function on my ladder was replace y by natural log of y. I've done that. It looks like this. That's still a little better, but that is still concave up. Then I tried replacing y by -1 over square root y. That looks like this. And I tried replacing y by -1 over y. So this pattern here, so this pattern here is definitely concave up. This one, it's a little hard to say. And by the time we get to this one, it's definitely concave down. So my transformation is working. It didn't seem to hit an optimal point very well. This one's probably the best, but it still has a lot of wiggle. It's not very linear. So on my ladder, rather than keeping going here, I might switch over and try to make a replacement in x. What if we replace x by x squared or by x cubed and so on? So I have done that. Here is replacing x rather by x squared. It's still concave up, but not as strongly. Here's replacing x by x cubed, just maybe very slightly concave up. Here's replacing x by x to the 4th. And by the time we get here, the data has been basically linearized. So of all of the models that I've looked at, 1, 2, 3, 4, 5, 6, 7, 8 of them, I think y versus x to the 4th is the one that I like the best. So back here, just in terms of keeping track of what is happening, we need to reduce concavity. And trial and error. Shows making a new variable x, which is the old x to the 4th power, is most linear. So then what I have done, I'm not going to do it here just to save time, but I've taken this y versus x to the 4th graph, asked Excel to form a trend line, and it did. And this is in terms of the new variable x, which is just the old x to the fourth. And so I can just come here and immediately read off what the form of my model is. It's y equals 0.2431 x to the fourth plus 145.69. There's no reason to assume that this constant would have to be 0. It's that when x is 0, I'm talking about the year 1940, and the number of fish harvested in that year probably wasn't 0. So okay, this is as good as I can do with y equals x to the fourth. What I've done now is go back to the original data and generate a prediction. So I've taken this model form and fed in each of the x values, taking the fourth power and so on, and generated these predictions. And then over here, I've graphed both the actual data value in the blue and the predicted data value in the kind of the lavender pink. So you can see a pretty decent fit. But if I wanted to look more closely at the fit of the model, again, I'd want to do a residual plot. So here I've taken the actual data values minus their corresponding prediction and gotten these numbers. These are my errors. And here I have plotted the errors as a function of time. So I know from this picture that my model is not bad, actually. From this picture, I'm looking at the residuals and saying, does this pattern look very random? And not maybe so much, especially here at the beginning. You notice that all of the residuals are positive for a while, and they have this weird quadratic shape in them. That doesn't look so terribly random. So here's kind of the conclusion, and I'll leave it there, that this is not a bad model. But the residuals still show a slight pattern that has not been captured. There still is more information in the errors that another model, a better model, could perhaps get. So just to note what's going on, when I say that, I'm plotting, we have plotted x versus the residuals and saw some trend that looked like this, basically. And I'm most concerned about right in here where there's a run of positive residuals, but not too bad. It's always a trade-off. How hard do you want to work versus how good of results do you need? And I think that, yeah, that will be good. We'll stop here. Thanks.